Let's talk a little bit about energy in simple harmonic motion. Here's my mass on a spring system. And at equilibrium, again, the net force on this object, this mass, is 0. Now, if I pull this object down, I've stored some energy in the spring. And so now this system has some potential energy, elastic potential energy in this case. As soon as I let go, we'll see that energy converted into kinetic energy. I could do the same thing. I could lift it up here. Again, now we've got some stored potential energy. When I let go, we'll see that converted into kinetic energy. And so we see in this system, we see energy moving back and forth from potential energy to kinetic energy. Now, it's a little bit surprising, but again, we can actually ignore the gravitational potential energy in this system and just focus on the spring potential energy. The difference between this in a vertical plane and if it was moving horizontally is just that the location of the equilibrium position moves. It changes. If I was to take the system to Jupiter, where gravity is stronger, then the new equilibrium position might be here, but the mass would still oscillate around that point. Again, the mathematical derivation of that is given in the book. I will not give it here. The point is, we see energy moving between kinetic energy and elastic potential energy. Over here, we see the same thing. Only here, when I move the pendulum over here, we have energy stored as gravitational potential energy. When I let go, it will be converted into kinetic energy. Here we see energy being converted back and forth from kinetic energy to potential energy to kinetic energy and back to potential energy, and so on. If there was no friction in this pivot and no air resistance, this would go on forever. There is friction and there is air resistance, so eventually this will stop moving. And all of that potential energy will be dissipated as thermal energy. For right now, we're going to focus on systems with no friction and no air resistance. Looking at the PowerPoint, here we see a mass on a horizontal surface. Again, it's identical for a mass on a vertical spring. And this graph right here is the same whether I'm talking about a mass on a spring or a pendulum. This line here in the middle represents the equilibrium position, and these 2 points here are our turning points. If the object is at the turning point, all of the energy is potential energy. As the object is released, its speed increases, meaning its kinetic energy increases, while its potential energy decreases. Here we see potential energy decreasing and kinetic energy increasing. The total energy remains constant. At the equilibrium position, there is no potential energy, and all of the energy is kinetic. As it begins moving back towards the turning point, it slows down, and that kinetic energy is converted back into potential energy. Now, we know that for a mass on a spring, the energy stored in that spring is 1/2 kx squared. We learned that in a previous segment. We've also learned that kinetic energy is 1/2 mv squared. And so we can write that the total energy of the system is simply potential plus kinetic. Not too bad, right? This is just conservation of energy. It's exactly the same thing that we learned in Chapter 10. We're just applying it to a specific situation here. Now, note that at the turning point, all of the energy is kinetic. And so the total energy is 1/2 Ka squared. Recall that A is the amplitude, right? And so A is the maximum stretch of the spring. So the total energy is 1/2 times K times the maximum stretch of the spring, which makes sense because when the spring is at its maximum stretch, it's not moving. So all of the energy is potential energy. There's an important point here. Often when I say this, students think, oh, well, that's only true at the turning point because I'm evaluating X at the turning point. No, that's just the total energy, right? Recall from this picture here that the total energy never changes. So whether the mass is here, 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 or here, the total energy is always 1/2 Ka squared because the total energy never changes. As I described in a previous segment, we're focusing here on simple harmonic motion because simple harmonic motion is well described by sines and cosines. In this case, in this class, we're going to focus on cosines, right? So we're going to focus on motion that starts above the equilibrium position, or starts on the positive side of the equilibrium position. If we always start at the turning point on the positive side of the equilibrium position, then our motion will always be well described by a cosine. And I'm just going to go ahead and constrain our discussion here to that. Notice if we were to start down here, we would need a different function to describe it. And if you look online, it's easy to find that. It's not that hard, but I'm just not going to deal with that. I'm going to deal with very specific situations. T equals 0 when the object is at the maximum displacement on the positive side of the equilibrium position. If we do that, then we can describe this motion, we can describe the position of the object with a cosine function. And here we see this, right? And so we were saying x here, if we're talking about vertical motion, we probably would use y. That's the traditional variable for vertical motion, but it kind of doesn't matter, right? This is just a position as a function of time. And so here we see this is the first complete cycle of the cosine function. Those of you that have had calculus will recognize that velocity is the derivative of position. If we take a derivative of this function, we end up with this function. Notice it is a negative sign. Negative sign. And here we have acceleration. Again, the derivative of velocity looks like a negative cosine function. Notice it is the inverse of this. Now, a couple of things to note. Previously, if you were wondering whether your calculator needed to be in degree mode or in radian mode, you could just look at the problem. If I gave you an angle in degrees, well, you know what? Your calculator better be in degree mode. If I gave you an angle in radians, well, then your calculator better be in radian mode. Not so easy to tell here, but I'm going to tell you that there's just a rule, and that is that if you are using those three functions, you need to be in radian mode. How can you tell? Well, this 2 pi right here says that we are scaling a complete cycle to 2 pi radians. Right? One cycle is 2 pi radians. So in order for this equation to work for you, your calculator has to be in radian mode. If you're in degree mode, you will get wrong answers even with the right physics. Recall that the very biggest the sine function can ever be is 1. The very smallest is negative 1. And that means that the maximum velocity that the object can ever have is this term right here in front, and the maximum acceleration is this term right here in front. Again, sine oscillates between negative 1 and 1, cosine also between negative 1 and 1. So the very biggest the velocity can be is 2 pi fa, and the very biggest the acceleration can be is 2 pi f squared times a. Again, a is the amplitude. If we're talking about a pendulum, we simply replace x with theta, v with w, and a with alpha for pendulum motion, right? Because a pendulum really is moving in a portion of a circle. And so we should use our circular motion variables for that situation. You know what? We'll focus mostly on the mass on the spring. It gets us all of the physics without getting into some of these more complicated circular motion variables. All right, I have a series of questions here to help us identify the various points in the motion. So here I have a picture, A, B, C, D, E, F, G, H, I, and each one of those is a snapshot in time of this motion here. Okay? Each one of those is a snapshot in time of a spring oscillating up and down. So here's the question. At which of the above times is the displacement 0? Pause the video. I'll see you on the other side. Well, this line right here through the middle represents the equilibrium position. That is where we define the displacement is equal to 0. So we say x is 0 or y is 0 or whatever variable we're using to describe that displacement. 0 is always at the equilibrium position. Remember, we get to pick our coordinate system, and we should pick a coordinate system that makes it easiest to solve the problem. It's easiest to pick 0 at the equilibrium position. So that would be A, E, and I. At which of the above times is the velocity 0? Okay. When is the velocity 0? Well, the velocity is 0 when the object stops briefly and changes direction. Recall that those are called the turning points. In this picture, I only see 2 of those. C and G are the turning points. That is where the velocity is 0. At which of the above times is the acceleration 0? Recall what equilibrium means. Equilibrium means net force is 0, and if the net force is 0, then the acceleration is 0 as well. So, where is the acceleration 0? At the equilibrium points. There are 3 of them shown, A, E, and I. At which of the above times is kinetic energy a maximum? Pause the video. Well, kinetic energy is at a maximum when the object is moving the very fastest. Where is the object moving the fastest? Well, as it moves through the equilibrium position. It's maybe even easier to see with the pendulum. With the pendulum, as it's moving through the equilibrium position, it's moving the fastest. It's the same with the mass on the spring. So where is kinetic energy a maximum? At the equilibrium position, A, E, and I. This one's a little bit tricky. At which of the above times is kinetic energy being transformed into potential energy? Pause the video. Make a definite decision here. It's going to help your learning if you commit to something. I recommend writing it down on a piece of paper. Okay, so if kinetic energy is being transformed into potential energy, we must be moving away from the equilibrium position, and the object must be slowing down. If it's slowing down, its kinetic energy is decreasing. Where is that energy going? It must be going into potential energy. So where in this picture is the object slowing down? Well, let's see. From A to C, it's moving away from the equilibrium position. It must be slowing down at point B. At point D, though, it's moving back towards the equilibrium position. It's speeding up at point D. I think it's also slowing down at point F. H is a tempting one, but again, I think at that point it is speeding up. So, where is kinetic energy being transformed into potential energy? At B and F, because at those points, the object is slowing down. Let's try the same thing for a pendulum. Now, in this case, we've got A, B, C, D, and E, and we should interpret this picture, this series of pictures, as a series of pictures of this motion right here. So for the pendulum, we're going to look at 1/2 of a cycle, from this turning point to this turning point. Okay. At which of the above times is the displacement 0? Pause the video, commit to something, write it down on your paper, and I'll see you on the other side. C, right? The displacement is 0 at the equilibrium position. That's what we define, right? We should just call the equilibrium position 0. That's at C. When is the potential energy a maximum? Well, the potential energy is a maximum when the object is not moving, because at that point, it has no kinetic energy. When is the potential energy a maximum? At the turning points. In this picture, that is A and E. At which of the above times is potential energy being transformed into kinetic energy? Okay, here we're looking for when is the object speeding up? Right? When is its potential energy decreasing and its kinetic energy increasing? Well, I think at point B, it is speeding up. D is often tempting for students, but notice at D, the object is slowing down. Let's do a numerical example. A 200-gram block is suspended from a vertical spring with spring constant 10 newtons per meter. The block is then pulled down an additional 10 centimeters below the equilibrium point and released. What is the speed of the block when it is 5 centimeters above the equilibrium position? Okay, so here's my picture. I've suspended my mass on the spring. I've pulled it down an additional 10 centimeters, and I've let go of it. And I want to know what the speed of the block is when it's 5 centimeters above the equilibrium position. So I want to know, right about there. Notice that's not at one of the turning points or at the equilibrium position. It's just somewhere in between. What do we know here? Well, if I've pulled it down 10 centimeters and then let go, then we know that the amplitude is 0.1 meters. The problem tells us that K is 10 newtons per meter, And further, it tells us that M is 200 grams, or 0.2 kilograms. Okay, there's a number of different ways we could solve this. Energy principles are the easiest. You know, last semester we saw that too. There's a lot of problems that can be kind of attacked with different techniques. Man, if you can do it with conservation of energy, it's almost always the easiest way. It's not a vector, it doesn't depend on time, all kinds of things make energy easier. So we're going to go ahead and do that. And I'm just going to go ahead and start with this statement here, that the total energy is equal to the kinetic energy plus the potential energy. The total energy is 1/2 Ka squared. The kinetic energy is 1/2 mv squared. And the potential energy can be written as 1/2 K delta y squared. My 1/2s cancel. I know A, I know K, I know M, I know everything here but V. Factor out my K. And now I can solve for V. And finally, I can put in my numbers. And so I got a number. 0.61 meters per second. Okay, not too bad. Again, there's other ways to solve this. You could have used the sine and cosine equations I gave you, but it's much more challenging, I think. This is a better strategy.